So let's go over thermochemistry, and to do that we need to review the thermochemical laws or thermodynamics laws. And so we'll go back and review some of the things you learned in your science classes in middle school and high school, but we'll go in a little bit more depth as appropriate. So you've heard of the first law of thermodynamics. This was from chapter 5 in the first semester course. Energy cannot be created or destroyed. Okay. Now, this is related to the conservation of mass. So the observation that mass is conserved in the chemical reaction. But when we get into nuclear transformations, some of the mass actually turns into energy. So it's a little strange. So this is a more broad version of that conservation of mass. It's really that energy is not created or destroyed. It can be converted into other forms of energy, and it can be converted into mass. And so this is the claim from this first law of thermodynamics, that the total energy in the universe is constant. And so we can split the universe into parts. And most of the time we deal with the system and the surroundings. The energy of the system, in our case, is the chemical reaction. So when we say like A goes to B, that's the system. And if energy goes into the system, it's endothermic. If it comes out, it's exothermic. And so that's the system, and then it's in contact with the surroundings. So if the system loses energy, then that delta U, that delta energy, is negative. And that's why we use the negative sign for exothermic reactions, because it left the system. And if it comes into the system, it's endothermic, has a positive sign. When you add that to what goes into the surroundings, you get a zero energy balance. So if energy left the chemical reaction, it went into the surroundings. And so we can use this equation. So energy is, definition is the capacity to do work. So that's kind of a strange definition. We're not really telling you what energy is. We're telling you what energy allows. We really don't know what energy is. So this is like the working definition of energy, but have you really thought about what is energy? It's a strange thing. Yeah. It's just the capacity to do work. Okay. It can be converted from one form to another. So we can go from like electrical energy to thermal energy. We can get objects moving, spinning energy, mechanical energy. And we do this all the time. So when we burn fuel at a power plant, we're making chemical energy, reacting it with oxygen. That makes thermal energy, so we have a lot of heat. Then we can boil water and make steam. So we have thermal energy now in the form of steam. And we can push that against a fan and turn a turbine and make it mechanical energy. And then that turbine can be hooked to a generator, which has a magnet and some coils, and a changing magnetic field generates a current, so we can turn it into electrical energy. And then we bring it to our houses. And then we run that electrical current through a resistor inside of a pot of water, and we have a hot water heater. It's really sad. We could have burned the chemical and made hot water right away. We lose energy at every one of those steps. And so if you have 100 joules of chemical energy, say in coal, you only get about 31 joules of electrical energy out of that. 31, yes. It's only about 31% efficient. So that's crazy. And so I'm a big fan of using like natural gas for any time you want to heat something. If you want to heat water, use a natural gas hot water heater. If you want to heat your food, natural gas, because we're using the smallest amount of fossil fuels to do the job. We have to use 3 times more of the fossil fuels to make electricity than if we just heat the food or the water or whatever, our house. Yeah. So anyway, so it can be converted from all those different forms. Transfer between the system and surroundings. Energy can be swapped from system and surroundings. And then energy, if we go way back in the universe, energy is the source of all matter. So this Einstein's equation, E equals mc squared, matter and energy can be transferred into each other. And so as we bring energy together and so on with collisions, you can create matter and vice versa. Then we get to the second law of thermodynamics. where we see that the entropy of the universe increases for spontaneous processes. And so notice we're talking about the entropy of the universe here, not the entropy of the system. So we define it later, but let's go ahead and define it now. What's a spontaneous process? It's a process that happens without any external intervention. So if you set a ball on the hill, and just let go of it and it rolls downhill. That's spontaneous. And so we can use this ball on a hill idea for chemistry. So you put two reactants together. If it's spontaneous, all you got to do is put them together and let go. Just like a ball on the hill. You put the ball on the hill and you let go. So that would be a spontaneous process. And the chemistry rolls downhill to lower energy. So And what causes it to roll downhill? It's this interplay of entropy and energy. So we're talking about entropy mostly today. So for irreversible processes, the entropy of the universe here is greater than 0. And we can break that into system and surroundings again. So the system would be the chemical equation. And then the surroundings would be the surroundings. And so this irreversible process this is a greater than. And so it would be equal to 0 for reversible. And reversible processes are just sort of controlled expansions. Like if I take a Coke bottle and I pop the lid off, the pressure drops from 3 atmospheres dramatically, instantly to 1 atmosphere. And any type of those discontinuities, where you've got pressure at 3 atmospheres with time, you pop the lid, it drops to 1 atmosphere. Notice how that's a sharp drop. That's an irreversible process. If I have a piston on the top and I very slowly let the pressure go down to 1, so it's a real smooth curve, that's the best model for a reversible process. Because the piston's moving very slowly and a small amount at a time. And if I push it backwards, then I can reverse the entropy in small amounts. And we get into that in PChem 2. So, a couple semesters from now if you're a chem major. All right. So don't get caught up in the reversible or irreversible thing right now. This means that as a result of all spontaneous processes, the entropy of the universe is always increasing. So we can have the entropy decrease in the system. So this could be less than 0. If this is greater than S system. Okay, so if I go down in entropy, that means the system's becoming more ordered, and we'll talk about what entropy means. The system could become more ordered if the surroundings become much less ordered. Okay, so we'll explore that a little bit later when we talk about freezing ice in your freezer. Okay, so the entropy of the universe is always increasing, and this leads to something that we don't talk about in chemistry or in science, but this leads to the metaphysical conclusion that the material universe cannot be infinite in the past, because we have solids, we have liquids. If the universe was infinite in the past, everything would be a gas, because the entropy of the universe is always increasing. If it's always increasing, then if it was an infinite time in the past, we would be at maximum entropy. We'd only be gases. Because we have planets, the stars, liquid water, and those kinds of things, those are really low entropy situations compared to maximum entropy would be all gas particles separated at infinite distance. So again, a metaphysical conclusion. Okay, then the third law of thermodynamics, the entropy of a pure, perfect crystalline substance at absolute 0 is 0. So notice this is the first time we've had a statement that actually put a number to something. So we're saying if you have a atomic crystalline substance, you cool that down to absolute 0, we're going to define that entropy of that perfectly ordered system as 0 entropy. This is mostly a theoretical concept. We can't get anything to 0 Kelvin. But we can calculate it. And then this is more useful as a reference point. So relative to this reference point, we can now calculate the entropy of everything else. And so that's really helpful. This allows us to put things in tables now because we have a reference point. It's like if you were given a thermometer and you could see the mercury in there or the alcohol, the little red liquid, but you didn't have any markings on it. You need a reference point, right? You need to be able to put the markings on it. And so this is the marking for entropy. At 0 Kelvin, we set that at 0 entropy, okay, for this particular substance. And then that allows us to make tables. So here's the tables of standard entropies for some liquids and solids and gases and some aqueous ions. So what trends do you see in this table? We're talking about broad trends at this point. Can I get you to close that? This is the part where you talk.
The entropy is getting smaller or decreasing?
With what?
Gas with like a solid.
Yeah, so gas has the highest entropy. It's kind of what I was alluding to earlier, that solids and liquids have smaller entropy. So in a system that has solids and liquids, like our solar system and so on, I mean, there's condensed phases. And the higher entropy would be gaseous phases. And so our planet, our oceans, our atmosphere, we're losing particles to space over time. And that's an increase in entropy. Okay, but sticking even to like water, solid water has a pretty low entropy at 38 joules per mole Kelvin. Liquid water is higher than that, it's close to 70. And then gaseous water, where you've got molecules flying around at all kinds of speeds, is 189 roughly joules per mole Kelvin. So we can track this entropy. And so what is entropy? A lot of people say it's a measure of the disorder or randomness of the system. So disorder is another term, measurement of the disorder or randomness of the system. But what is the word? I mean, how would you measure the randomness of something, right? I mean, you kind of think about randomness. You take a puzzle, and when it's put together, that's not random. And when you open the box and dump it on the floor, that is random. So what is that thing that we measure when we call it randomness? And I don't think this is well explained in any of the other courses. Okay, so I'm excited about this part. Okay, I will give you an idea of what randomness is. It's this next line here. It's the measure of the statistical options in a system. How many statistical ways, once the puzzle is done, that you can make that situation? Just one, right? Every piece is in its place and the picture is made, and there's no other way to make that. So that has a statistical count of 1. That's like the least random situation. The puzzle is complete, and you have one chance of doing that. What if I take 2 pieces out of the puzzle? Well, let's just do one, okay? Let's say it's a 100-piece puzzle, and it's missing 1 piece, okay? That's more random, right? Which piece did I pull out? It's a 100-piece puzzle, so I have 100 ways to make that situation. So there's 100 ways to make a 100-piece puzzle missing 1 piece, and that's more entropic. That has a higher entropy, because I could pull 1 piece, I could pull this piece out, I could pull that piece out. And so there's 100 ways to make the puzzle that's missing 1 piece if it's a 100-piece puzzle. Think about the number of ways that you could make a puzzle that's missing half the pieces, right? So you can pull the first piece, you can pull every other piece, you can pull the first 50, you can pull the last 50. There's a gazillion ways to make a puzzle that's half disordered, and that's going to be the maximum entropy. That's going to be the one that has the most number of ways to come up with that condition. So a puzzle missing half its pieces, that's going to be the most disordered state. That's going to be the highest entropy. Okay, so that now you have an understanding of how to measure randomness. It's the statistical way you can come up with that situation. Okay. And so it's just, in molecules, it's related to the various modes of motion of the molecules. And so you can have, like in water, we'll see water later on, we'll see all the different vibrations, and the molecules can be populated in all those different energy levels. And so what quantum state the molecule is in is a way to measure its disorder. And so there's certain ways that you can measure disorder, kind of like a puzzle. You put the molecules together in their quantum states. That's a certain way of doing things, kind of like a puzzle. And what if this molecule now is in an excited state? There's a lot of different ways to put a mole of molecules together where one of them is in an excited state, or when two of them are in an excited state, or three. And so just like our puzzle analogy, when you pull that piece out, maybe that's an excited state molecule. And if I have 100 molecules, there's a whole lot of ways to put together 100 molecules where half of them are in the excited state. Was it every other molecule? Was it the first 50? Was it the last 50? And all the different combinations in between. So just statistically, entropy is going to drive a lot of things in an ensemble of 100 molecules. So like total energy and enthalpy, entropy is a state function. So we can just take the entropy of the final situation and subtract the entropy of the initial situation. So in terms of state functions, we talk about energy states all the time. And so we might say, n equals 1, n equals 2, and these are energy levels or energy states. And if I find a molecule in energy state 2, it doesn't matter how I got there. I could have come down from state 3, or I could have come up from state 1. The path doesn't matter. All that matters is the state that I'm in. And so that's another sort of easy way to remember what we mean by state functions. It's just whatever state I'm in, that's my energy, or that's my entropy, or that's my enthalpy. Think of it as stairs. It doesn't matter how you get to the second floor. You could take the elevator, you could take the stairs. But when you're at the second floor, you have a certain energy. You're a certain altitude above the ground. Gravity's acting on you. It doesn't matter how you got there. It just matters what floor you're on. Same thing for molecules in their energy states. So when we say state function, you can calculate the change by just taking the final minus the initial. Okay, let's talk about spontaneous processes. So these spontaneous processes are processes that can proceed without any outside intervention. And so here we're going to talk about our chemical intuition. A lot of these pictures in the book, they talk about these gases and these evacuated cylinders and so on. And so here we have a gas at 1 atmosphere, and this side is a vacuum, evacuated, right? And we turn the stopcock, and you know what's going to happen. The gas is going to flow in and take up the largest volume that it can. And so it goes from 1 atmosphere in one side of the chamber to half an atmosphere, in both chambers. This, again, can be thought of as increasing the statistical options. Just think about a gas molecule. Before the reaction or the situation, it only had the space of B to move around in. Now it can move around in B and A. So it has twice as many options. And so the entropy increased. Every molecule can now move from A to B, whereas used to it just was in B. So you could think of entropy, again, with a statistical mindset. So this gas in vessel B will spontaneously effuse into vessel A, but once it's in both vessels, it will not spontaneously segregate. Like it's not going to just show up in B again, like just by itself, like all of the gas move into B. Is that impossible?
No.
It's not impossible. Statistically, it's not impossible. But it's incredibly improbable. Okay? And so just with natural forces, it's not going to just flow all back into B and we have all the gas in one half of the vessel, In fact, if you were to see that, you would start asking questions because it's so improbable. You would say something's going on here. There must be some external thing happening. Just like if you shook up your puzzle box and you dumped it on the floor and it went flop and it was all put together. Yeah, right. Just go to Vegas, right? So that's improbable. Is it impossible? No. But if it did happen, you would start asking your roommate, did you do something with the puzzle, like roll it up or something? How did that happen? Because that's not probable, And so you know more about entropy than you think. And so any organized system will spontaneously mix over time. And this isn't something that happens just with atoms and ions and molecules. This also happens with macroscopic objects. So if you had a jar of M&Ms and you had, like in this case, yellow and white M&Ms, and you had the yellow ones in first and you put the white ones on top, beautiful organized jar. But what's going to happen over time? Your little cousin or brother is going to tip it over. It's eventually going to mix. Once it's mixed, it's not going to spontaneously unmix. The same thing with atoms and molecules. Once they mix, it's really difficult to get them to segregate. It's just driven by entropy. This is the basis of solubility too. So if there's really no preference between like solute and solvent and solvent molecules, they will spontaneously mix by entropy. So we use this a lot in dissolving things and diluting things. But when we have precipitation, we have a spontaneous separation. That's an energetic effect, probably an enthalpy-driven thing. And so there's more to it than entropy. Entropy is higher when things are mixed, but sometimes things do segregate. And so neither Wednesday or Friday will get into what really drives spontaneous processes. It's the Gibbs free energy. So it takes into account the enthalpy and the entropy to give us a true measure of what spontaneous is. And so we'll look at spontaneous separations and spontaneous mixtures probably on Friday. We'll go over the test on Wednesday and we'll do some enthalpy calculations on Wednesday, and then Friday will be Gibbs energy. So this bulk thermodynamics, understanding entropy and enthalpy, the thermodynamics of reactions, this really did lead the Industrial Revolution. So I've got a typo in your notes. It says lead and allowed, so just scratch out lead. Okay. So thermodynamics allowed a clever use of steam power. We understood what gases would do, turning turbines, pushing pistons, and that led to the Industrial Revolution. So this was a modern triumph of science, beginning in the 1700s, really developing in the 1800s, and transformed the world. And Boltzmann in the 1900s, Boltzmann and Planck and others began developing quantum mechanics. Actually, Boltzmann in the 1800s, but then Planck and others used his math and applied it to quantum mechanics. And quantum mechanics, it started to try to derive enthalpy and entropy using statistics. So the phrases and verbiage I've been giving you already is this statistical definition of entropy that Planck and others developed. Okay, so I was kind of inserting that in your head that entropy was driven by statistics, but that was not the case or the belief or the understanding for the Industrial Revolution. They didn't really know what entropy was. They thought it was related to disorder because gases had more entropy than solids and liquids, but they didn't have a really good molecular view of entropy. And so Boltzmann and Planck and others put that molecular view on it and showed that it could be driven by statistics, but Einstein was skeptical. And this is where his famous quote comes from. You might have seen this written in other ways where he said, God does not play dice. This is what he was talking about. He said, quantum mechanics is worthy of regard, but an inner voice tells me this is not on the right track. The theory yields much, but it hardly brings us closer to the old one's secrets. And so that's what he's talking about. That's his, in that phrase, he's talking about God. And he says, I, in any case, am convinced that he does not play dice. And so what does that mean, not play dice? He's saying this statistical derivation of entropy and enthalpy, he just wasn't convinced yet. But once they nailed the sort of the equilibrium constant using statistics, then it pretty much made a believer of everybody. Not that God plays dice, but that statistics was valuable for thermodynamics. So on the molecular scale, these are some of the properties that Boltzmann described using this concept of entropy on the molecular level. He said molecules exhibit different types of motions. So translation of the molecule would be the whole molecule moving in space. So if this whole molecule moves in this direction, that's translation. Okay? The whole molecule can rotate around the z-axis or the x-axis or the y-axis. So there's only 3 rotations. So it can, in a Cartesian system, which really any system can be turned into a Cartesian system. So it can rotate around z, around x, or around y. And there's only 3 rotations. And then however many atoms there are, you can have lots and lots of vibrations. So in water, there's 3 atoms. You take away the 3 translations, the 3 rotations, you have 3 more degrees of freedom, and those are the vibrations. So these are the pictures of the vibrations. So this is a symmetric stretch. And so like if my head is the oxygen atom and my hands are the hydrogens, that's this stretch. So they're moving away from the oxygen. And then the asymmetric stretch is the third picture. So one is compressing while one bond is compressing while the other is stretching. And so that's my best dance move on the floor. People say, what's he doing? That's the asymmetric stretch. Okay. Yeah, it's better than the sprinkler, you know. And so then you have the bond bending motion. So this just changes the angle between those bonds. And so we call that a bend. Now, if I have 100 water molecules, I have 300 vibrations because there's 300 types of vibrations. And if one of those molecules has a bending mode that's excited, like instead of bending this slowly, it's bending this slowly, then it's excited. And there's, again, 100 molecules. So I have 100 ways of making that situation where I have one molecule excited in the bending mode. But I have 300 options. And so you can think of the statistical way of building this system where I have lots of vibrations being excited. So that, again, once I start to excite vibrations, then the entropy goes up. But vibrations are pretty high energy. So let's talk about rotations. Rotations are pretty low energy. But if a molecule is in water, like if I have water in water, it really can't rotate. And so I can't really have excited rotational states. But if I get that molecule in the gas phase, now I can rotate with 1 quantum or 2 quantum. And so the gas phase naturally has a lot more entropy, have a lot more rotations, a lot more translations, because in the liquid state, my molecule can't really translate. It's stuck. But if I get it in the gas phase, it can now translate. So translation and rotation are really the source of a lot of entropy in the gas phase. The liquid states and the solid states are not that different, really, in terms of their entropy. And so then when you don't have any rotation, no vibration, you have a perfect atomic crystalline solid, then it's defined as 0 entropy. So this is Boltzmann. He came up with this equation of entropy with the statistical counting of states. You've already used Boltzmann constant, but you used it in terms of the gas law. So if you take Boltzmann's constant times Avogadro's number, then you get the gas constant R. So that's pretty convenient. You've been using Boltzmann's constant the whole time when you use the gas constant. His derivation of entropy was so famous that they put it on his tombstone. So that's pretty cool to have your tombstone have an equation on there, and there's his constant in that equation. So
Did he ask for that?
I don't know. Yeah. Yeah, that's right. That's right. I don't know. Yeah, who knows? Yeah, but anyway, that was one of his proudest accomplishments. Yeah, very troubled life. He was, he's a sort of a, what I want to say, kind of a cautionary tale of the science is settled, right? You hear that a lot now with climate change and a bunch of other things, or COVID or whatever. Whenever they're trying to shut down debate, they go bang on the table. The science is settled. Quit questioning. Okay, he believed that particles, atoms, molecules existed, but the science was settled. That's not true. Okay, guess what? He was right. And he was so hounded by the science was settled folks that he was bipolar, and in one of his depressive states on vacation with his family, he committed suicide. So again, cautionary tale. When people are beating the table saying the science is settled, that's not how science works. Okay, all it takes is one person to be able to prove something like this and create a whole new revolution of science and brand new findings and so on. Science, we don't vote in science. It's not, you prove, you do research, you collect evidence. Okay, so whenever they trot out, we got 1,700 scientists to sign this piece of paper that says this and that's not how science works. So dig into the data, dig into the conclusions, make sure the conclusions tie to the data. That's how science works. So, cautionary tale. Okay, let's look at spontaneous processes some more. So they're temperature dependent. So processes that are spontaneous at one temperature may be non-spontaneous or go in the reverse direction at another temperature. So above 0 C, it's spontaneous for ice to melt. Below 0 C, the reverse process is spontaneous. So let's figure out how we make ice in the fridge, right? Which of these has the lowest entropy? So ice is on the left. We just looked at the table and there's water. Okay, so which has the lowest entropy? Which is the most ordered?
Ice.
Yeah, very good. So low, well, that looks like low entropy, low S, okay? And notice we said that in a spontaneous process, the entropy of what always increases? We have three options: the entropy of the universe, the system, or the surroundings. The universe. The entropy of the universe increases. So we could have our system, which in this case is ice, have a decrease in entropy, and this be spontaneous. So this is saying that entropy decreased spontaneously, but this was for our system. How do we get our system to decrease in entropy? How do you make ice in your house?
Put it in the freezer.
You put it in the freezer. So you put water in the freezer and it's cold. How is that freezer cold?
Electricity.
Yeah, right, okay. So something's going on with electricity. There's a compressor involved. There's a thing called a heat pump, and it's pumping heat from the freezer to where? Into the kitchen. You feel the back of the freezer or the fridge, you feel warmth, right? That's the heat from the freezer and the fridge. It's pumping the heat out into the kitchen. Where does that heat go? It increases the temperature of the room air. That's an increase in entropy. So entropy goes up with temperature. And all we have to do to make ice is to get the entropy of the room to go up more than the entropy of the water goes down when it freezes to ice. So we're still, the entropy of the universe, the kitchen plus the freezer has increased. So the kitchen's entropy went up more than the ice went down. And that's how we make ice. So the system can decrease in entropy if the surroundings increases more. And so that's how we're using entropy to make this spontaneous decrease. We're using the entropy of the universe increasing to make a small local system decrease its entropy. And we do that all the time.
How long until the heat death of the universe then?
Oh, a long time. Yeah, we have a long time because we have, like I said, condensed phases, planets, stars, water, and so we've got a long time for the battery to run out. So entropy in physical states, we've kind of talked about solids, liquids, and gases. Entropy increases with molecular motion. So gases move the most. Liquids move more than solids. So again, if something's fixed in a solid matrix, like this is ice, a perfect crystal of ice, we have hydrogen bonding networks holding that water molecule in place. It can't really translate. It can't really rotate. So there's very little motion in the solid, especially in a crystal. Then you let it slide past each other. You got more motion in a liquid, higher entropy. More motion in a gas, even higher entropy. Solutions are a little weird. Okay, and aqueous solutions show some exceptions. So when a solid dissolves, the entropy increases because you have mixing. And there are a few aqueous exceptions. Look at these down here. So aqueous nickel 2+ has a negative entropy. And that is crazy, okay? And again, these are sort of like reaction entropies. So you have nickel, salt, whatever, and the nickel cation goes into water. So you have water. When you make that aqueous, then the water is organized around the ions. And so we've reduced the order, we've increased the order of the water. So this water molecule is free to move around, do whatever it wants. But these water molecules are less free. They're stuck to a cation. And so this situation results, because of how we chose our reference entropy, this results into this confusing negative entropy. It's not that these things are at less than 0 Kelvin. It just means that they're more ordered than the system apart. Like water and nickel chloride apart have a certain entropy. You move them together and you make nickel chloride aqueous, and you have a negative entropy for the nickel part. You organize the water solution around the nickel and chloride ions. We can look at entropy changes, and generally entropy increases when you go from liquid to solid. Entropy increases when gases are formed from liquids and solids, when liquids or solutions are formed from solids, when the number of gas molecules increases. And so if you have, let's take water, so H2O liquid, and you make two H2 plus O2, so we need 2 waters. So we have three moles of gas, which is a huge delta S. So entropy is increased quite a bit in that situation. And then if you increase more particles, then the entropy increases. So let's do some calculations. So here's our standard entropy tables. You can find these in the back of either one of your books. And so we'll do a calculation in a second. It's just showing you as the molecule gets bigger and more complex, the entropy increases. And so here, let's do the calculation. So for a reaction, it's products minus reactants, taking into account the number of moles of each of the species. Okay, so let's practice on this. So here's the reaction. 2 moles of hydrogen plus oxygen makes 2 moles of water. And so we go to the table and we find the reactants and products. So we start with the products. So water, gas, 188.8 joules per mole Kelvin times 2 moles. And so the moles cancel, and we end up with joules per Kelvin, 2 times 188.8. And we subtract the hydrogen number, so minus 2 moles of that. And then the oxygen number, minus 1 mole of the 205. And so our result is minus 88.6 joules per Kelvin. So that's the delta S for this reaction. Okay, now that is you can pair that with the moles in the equation. So that's the entropy change for producing 2 moles of water, or the entropy change for producing 1 mole or using 1 mole of oxygen, or the entropy change for using up 2 moles of hydrogen. So whenever you go back to using this as a mole ratio, you take into account the moles of either species in the reaction. We'll get some practice with that on Wednesday. Notice that the entropy decreased when we added hydrogen and oxygen to make water, because we took 3 particles and we made 2 particles. And so we have fewer particles, we have fewer statistical options, the entropy went down. And yet this is a very spontaneous process. This is how we push the space shuttle up into orbit. Okay, so that big orange tank on the front of the space shuttle, I know it's been a while since it's flown, but do y'all remember the space shuttle? Remember pictures of it? Okay, you've got the solid rocket boosters, the 2 sticks on the side, and then that big tank in the middle had a tank of oxygen and a tank of hydrogen. And those went through the main engines of the space shuttle, and it produced a ridiculous amount of thrust, like 75% of the thrust. Even though those big solid rocket boosters looked impressive, the main engines on the space shuttle were really producing a lot of the thrust. And it was hydrogen and oxygen to make water. So that big cloud of smoke coming out of the back of that thing was mostly steam, because it was hydrogen and oxygen making water. And definitely spontaneous, right? We didn't need any outside intervention. Once we got those gases flowing, then they reacted. So there must be something more to spontaneity than entropy, and that is the enthalpy. So it produced such a great temperature change. It was an exothermic reaction that the water was at a much higher temperature. And so that was really what drove that process. So because it was a decrease in entropy, that actually hurt the reaction a little bit in its spontaneity. But it was so exothermic that it was strongly spontaneous. And we'll explore that more this week. Let's calculate for another one. So let's do the combustion of ethanol. Or methanol. So we have CH3 OH plus O2. Yes?
In these questions, do these the enthalpies or the entropies will be given to you for each of the?
Yes, you'll have to have a table. Yeah. Okay, so if I give you the combustion of methanol, you've got to be able to balance this chemical equation. Okay? So we've got one carbon on either side. That's good. Let's save the oxygens for the end. We've got 4 hydrogens. They come in pairs over here, so we have 2 there. So now we have the 4 hydrogens. And so then add up the oxygen. So I've got an O2 here, and I've got 2 oxygens there. I've got an O2 there. So I just need 2 O2s. Nope, but I've got 1 here, 1 oxygen here. And so I only need 3 here. So how do I get 3 oxygens when they come in pairs? Three halves. You could do that, but it's not pretty. Okay, so let's get rid of that by doubling everything. And so we're going to put a 2 here. If I multiply 3 halves by 2, what do I get? 3. So scratch that out. 2 there, and let's put 4 here. Okay, so that's a way to get to that balanced equation if we don't want 3 halves in there. Okay, you could stick with 3 halves and then just multiply your numbers by 3 halves. So that would work, but you could also double it. So let's do it for this equation as written. So products minus reactants. So I have 2 moles times the CO2 number. No way, it's not in the table. Shoot. Somebody go to Wikipedia and look up the entropy of CO2. Okay, 4 moles. Just Google entropy of CO2, standard entropy CO2. Okay, water gas, 188.8.
51.11.
51?
0.11.
That's good enough.
Calories left.
Oh, calories? No.
Oh, you're looking for Kelvin?
Joules per mole.
Oh, joules per mole? Oh, shit.
Yeah.
Okay, hold on.
All right. And then we're going to subtract our reactants. So I have minus 2 moles.
213.79 joules.
213.8. Okay. Joules per mole Kelvin. Thank you so much. Okay. And then the methanol is 126.8. And then we minus the 3 moles of oxygen of 205.0. Okay. So don't drop your negatives. These are all joules per mole Kelvin. So I'm just going to do this. So someone with some fast fingers, calculate that for us. Anyone?
1.2.
Positive?
Yeah. Because you add the first 2, right?
Yep. and it's joules per Kelvin. And does positive entropy make sense? Let's look at the number of moles of gas. So we have 5 moles of gas here. So 2 moles of methanol, 3 moles of oxygen, and we're producing 6 moles of gas, CO2 and water. So yeah, that definitely makes sense. It should be a positive entropy, so that it should increase. So that's the main thing driving the entropy of this reaction is going to be the change in number of moles of gas. And then it's going to be exothermic. It's going to generate heat, and that's going to drive its spontaneity even more. Yeah, so we'll see you next time.